So now we'll start chapter 10, starting with correlation first. And we did some correlation in chapter, I believe, 2 or 3. But we will know how to calculate correlation or linear correlation coefficient. We call it R. Okay, so we did say that we and for sure we will study just only the simple correlation, which is we have two variables, x and y, or just we can say like two variables, x and x1 or x2 and so on. Okay, so we did say that correlation is just how to find the relationship between two variables, right? So we will not study like causation, which one will affect the others. So just or only we will find if we have any relationship between two variables, or basically any linear relationship. So just we will study the linear relationship, which is mean that we can represent this relationship as like a straight line. So if we have the scatter plot and we have our data like this, for example, then we can say that, okay, yes, this is linear, this relationship is linear. So we did study three things, if you remember. The form of relationship, we did say we have, so we say the form could be linear relationship or non-linear relationship or no relationships, right? So this is, we can say linear or non-linear somehow, and then no relationship here. Okay, so linear relationship, non-linear, no relationship. So this is the form. And then we did say the direction of this relationship, which is we say that the value of R, if this value positive, then the direction will be or the relationship will be positive. So as one of variable increase, the other one will increase too. If the R, so might be the relationship like this, which is as one of those variable increase, the other one will decrease. So the direction will be what? Or the relationship will be negative. So in this case, it will be the value of R will be negative. Okay, so form, the form of relationship, linear, non-linear, no relationship. Direction, positive or negative. And then we study also how strong this relationship will be. And we did say this value of R between -1 and 1. As we get closer to 1, the relationship will be stronger. And as we get closer to 0, the relationship will be weaker till R equal to 0. Remember, when R equal to 0, we did say no linear relationship. No linear. We cannot say no relationship. We can say no linear relationship between those two variables. So if you look here to this scatter plot, somehow we can represent this data with this straight line. As one of those variable increase, the other one increase. So that this will be positive relationship. And also remember, as this dots here closer to the straight line, as this dots here and here closer to this straight line, as the correlation will be stronger. as this dots will get like farther from the straight line, then the relationship will be weaker. And here you can say this is R equal to 0.859, which is a strong relationship. Okay. So now for this one, we can represent this one using this straight line, maybe like this. For sure, this is, so the form is linear. The direction is, as one of variable increase, the other one will decrease. Then this is negative from this sign here. And if you look to this dot closer to the straight line from this one, so if you look to this one, 0.85, for sure this one will be greater, which is almost equal to 1, 0.971, which is very strong correlation between those two variables. So here, the form is linear, the direction is negative, and strength is strong. Strength with the strength of the correlation as this value gets closer to 1. When I say closer to 1, I mean positive or negative 1, right? So as this value gets closer to 1, stronger. As it gets closer to 0, it will be weaker. If you look to this one, just from looking, we can say this is no correlation between those two variables, right? Clear. From scatter plot, even we can say no correlation. From this, if we have only this value, we don't have the scatter plot, we can say no linear relationship. But since we know now the scatter plot, we can say, oh, no correlation between those two variables, okay? So from value here, we can say no linear correlation or no linear relationship between those two variables, okay? But since we know the scatter plot, we can say no correlation, okay? That's why the first step we should do when we study the relationship between those two variables, to do what? Scatter plot first. So if we find the scatter plot like this, we don't waste our time and go calculate this value, right? Since we know this value will be very close to 0. So now if you look to this one is, the relation in this one is have like, it could be non-linear relationship, right? So it's some kind of quadratic, or right? So this is non-linear. So if we study the form, we can say, oh, we have non-linear relationship. But anyway, if we represent this using a straight line, might we get line like this? I don't know, might be like this. Still, we have some, if we consider this as outlier, the rest is not really far from the straight line, and we got this R equal to 0.33. So if we eliminate this value, might the correlation will get really higher. Maybe we'll get to like 0.6 or even almost 0.7. Okay, so if we take this one and this one, the correlation will be very, very high. So if we eliminate those two values, we might get straight line like this. Okay. So we did say, as a summary for those, we did say positive, negative, linear, positive, linear, negative, non-linear, no correlation. Okay. And then we will see how to calculate the factor of this correlation. Okay, so this is, we call it correlation coefficient or sample correlation coefficient. Okay, so for sure it will be linear. Okay, so R, if want to just use it, the quick formula, maybe if you want to write this one, so it's much easier. R equal to SXY divided by square root of SSX square root of SSY, where SXY equal to summation XY minus NX bar Y bar, or you can use this one, summation X summation X minus X bar Y minus Y bar. Okay. O and S, SX equal to summation X square minus NX bar square, or you can use this one, summation X minus X bar square. And then SSY equal to summation Y square minus NY bar square, or you can write it as Y minus Y bar square. We'll take example in details. But I like to use those formulas to calculate. It's much easier. Okay. So the first step we can do here to know if we have linear correlation or not. So how can we know? So this value R will give us if there is a linear correlation between two variable or not. Only linear. So the coefficient of correlation R, just studying the linear relationship between those two variables. So here we have some notation. So N will be the sample size. So it will be like this here, X and Y, the data, and we have some values here. So the number of those values will be N. And then this is, we call this summation. Okay. And this is sum of X. So if we have, let's say 1, 2, 3, 4, 5. So then this summation equal to 15. Then we can say summation of X equal to 15. And for example, 2, 4, 6, 8, 10. And then we say summation of Y equal to 10. We have 10, 20, 30, for example, right? And then summation of X square, just we take every single value of X and square it. So it will be 1, 4, 9, 16, and 25, and then add them up, there will be 55. So we can say summation of X squared equal to 55. Remember, summation of X square equal to 15 square, not equal to summation X square. Okay, so summation X square is not equal summation X all square. Those totally different values. Okay. And then when we have summation x times y, we have to do it here, for example, like this, x, y. So we multiply this and this together. We say 1, 8, 18, 32, and then 50, right? And then we add those values up. This will be summation of x. So this R will be, call it linear correlation coefficient for a sample. Since when we study the population, we have the other one, we call it rho. But for now, I don't. So for now, just R is the linear correlation coefficient for the sample. Okay, and yes, here you go. The rho is linear correlation coefficient for population. Okay, so this is, we call it rho. So now this one here, they say, okay, what if we have like a collection sample of data, how can we find this one? The first thing, we should be using simple correlation sample. So we cannot say like to study the correlation between two variables and we have biased sample, for example. And then second thing, we do what? Scatter plot. And we can say that we have some a straight correlation between those two variables. So if we have a scatter plot, we did say if scatter plot like this, so we don't go even and study this correlation. We know that no linear correlation between those two variables for sure. So to go and find the correlation, we should have somehow linear pattern, right? Or we can represent the data using straight line. So if we have outliers, we remove those outliers before we study. Okay, so if we have outliers, those outliers must be removed if they are known to be error. So sometimes, sometimes like a human error. So instead of writing 10, I did write 100. So we will have like a very far number, and we know for sure this number is not right. So for example, for the height for individual in centimeter, we say like 400 centimeter, which is, it's not possible, right? So we know for sure this is outlier or this is just a mistake. So we should remove all those outliers. Okay, so and then I don't know, I told you, you can use this formula or you can use this one, as I did say, summation xy minus nx by bar divided by square root of summation x square minus nx bar square, and then the same summation y square minus ny bar square. And remember, we did this one, r equal, the top is xy, we can represent it, and here ssx, ssy. Okay, or you can use this one, basically this and this exactly the same. Exactly. So just what I did, I just simplified this formula a little bit. What I did, so I divide the top, every single value in n. So we divide by n here and n here. Okay. So this will cancel this. We left with this first one here. And then this one, summation x divided by n, is basically x bar. And if we do y bar here, we have to multiply by n. So n times n here. So this is y bar, and this is the n I add here. So basically, this formula and this formula exactly the same, but the second one is look maybe nicer a little bit. Okay. Also, we can use the Z value to calculate R. Remember, Z equal to what? Zx equal X minus X bar divided by S, and Zy equal to Y minus Y bar divided by S for Y. So this is 2 for SY, and this is SX maybe. Okay? And so this is exactly the same idea. It's just exactly the same. This formula, just they simplified. Okay. If you have defined the correlation, round this correlation to 3 decimal places. Okay, 3 decimal places. So we can compare those values to the critical value you can find in our table, or even using technology. Also, we can use the B value. When we have B value less than or equal to alpha, then we can say, okay, we have correlation. So if this B value less than alpha, which is alpha most of the time equal to 0.05. So this is the default value equal to 0.05. But if B alpha is greater than 0.5, then, or sorry, 0.05, then we can say, dog, we don't have correlation between those two variables. And we will see when we use technology in a second, how can we find those values. Also, we can use table. Okay, you can use table to find the correlation. Basically, if we have the value of R, this one, this one, R greater than, so we did say, if you remember the first week, so this is -1, and this is 1, and this is 0, and we have critical value here. So this is the critical value. So the critical value, the critical value, it will be positive and negative. So let's say 0.8 and -0.8, this is critical value. So if we have any value of correlation here or here, we will say that we have correlation, which is greater than or equal to critical value. We have correlation here, we have correlation here, and any value between -8 and 0.8, we say what? No linear correlation. No linear correlation between those two variables, because we don't know if we have a non-linear, right? So R is just giving us the linear correlation between those two variables. Also, we did mention before that this R between -1 and 1. Okay, so this is one thing. And then if all values of either one of those two variables converted to different scale, the value of R will be exactly the same. So imagine that we have this XY, 1, 2, 3, 4, 5, and then we have 7, I don't know, 6, 3, 2, 1. And then we multiply the X variable by any number. So if we say, okay, we have now the new variable, X star, for example, equal X times 2. It will be 2, 4, 6, 8, 10. And then we have the same Y, which is 7, 6, 3, 2, 1. So if we calculate R here and here will be exactly the same, okay? And remember, when we study correlation, we don't have any variable. We can, I mean, we will not study causation, and we will not say that, oh, this variable will be affected by this. So if we do, for example, if we do this scatter plot and we put X here and Y here, or change them, we put Y here and X here, is the same. And this value will be exactly the same. So if we study, if we put those values under X and those values here under Y, it will be exactly the same value of correlation. Okay, so X and Y, just we can choose like X for Y values and Y for X values. That's okay. And we remember that R will measure the strength of the linear relationship, right? So we say that, okay, as get closer to 1 will be stronger. As it get closer to 0, it will be weaker. R equal to 0, no linear relationship. So, okay, we cannot say no relationship between those two variables. We can say just no linear relationship. And then remember, let me write the formula down again. Summation xy minus n x bar y bar. And then we have S, or let's write it down. Summation x square minus n x bar square. And then here we have summation y square minus n y bar square. Right? Or we can also, I don't know, we can use this formula too. Summation x minus x bar, y minus y bar, divided by square root of summation x minus x bar square, and summation y minus y bar square. So look here in this formula tab, x bar, y bar, x bar square, y bar square. And since we know x bar is sensitive to outliers, look here, y bar, x bar, y bar, right? Since we know the x bar and y bar very sensitive to outliers, then even R, they will be sensitive, okay? So R is very sensitive to outliers. Okay, so now if we have this two variables, and we want to study the correlation between those two variables, we can do it like this. If we want to do it manually, X, we can use this as X, and then Y. Okay, so we have 5, 6, 4, 4, 5. Okay, and then we have 6, 9, 3, 2, 11. And then remember the formula here, what we need. So I all the time I use this one. So do we have X bar? No. Then we calculate X bar. X bar equal to what? Summation X divided by N. So you add now here, come here, and add the summation. So you add those values up, you will get the summation. Okay, and here. So let's do, and then the next one, what we will do. So go back to the formula, calculate X bar, and then calculate Y bar equals summation Y divided by n, and then you need x times y. So we have to find x times y, and then we have to find x squared and y squared. I think I already did write them down, but we need those, and we have to find the summation here. Okay, so now if just by using technology, we can find those values. Let me go and find this one using technology. So come here, analysis. Okay, here. Go till you find correlation and regression here. Correlation and regression. Okay, and then we have some values here. Let me just clear it. Okay, so if we have those values, which is 5, 6, 4, 4. Oops. 4, 4, and then what? The last one is 5, right? And then the second variable, which is 6, 9, 3, 2, 11. Okay. And then here, don't worry about this one. So you can use 1 or 2. That's okay. Not 1, 1, 1 here. Okay. So now this is those the values. So the first one here in the top is the sample size, n. And then we have degree of freedom equal to 3, which is 5 minus 2. And those two, we did say x bar and y bar, because we know the value of a statistic x bar and y bar. Then this is 5 minus 2 equal to 3. And then this value of correlation equal to 0.795. Okay. And the correlation, and the critical value, so 0.878, right? And we did say we must get this value here greater than or equal to, greater than or equal to this one, right? And also we did say this B value must be less than 0.05. 0.05. And since this value greater than 0.05, then we can say, okay, we don't we don't have linear relationship between those two variables. Okay, so we can say no linear correlation. Okay. So let's go back here. Oops. So this is the value of correlation. Okay. And B value equal to, so this one greater than 0.05. And if you see -1 to 1, and we have 0.878, which is negative, and here we have this critical value, right? 0.878. And our value, so we did say any value here, no linear correlation. And here we can say we have correlation. Okay, so if you look to our value, which is somewhere here, So we can say, okay, no linear correlation between those two variables, and this is clear from the B value here. Okay, so this is how can we calculate this one. So we had X here, and we have Y here. And then second, we calculate X squared. So it's the 5 squared equal 25, 6 squared, 36, 4 squared, 16, 16, and this is 25, right? And then the same here for Y squared. So 6 squared will be 36, 9 squared, 81, 9, 4, 21, okay? And then the next step, which is X times Y, which is this one times this one. So the first one, 5 times 6 equal to 30, 9 times 6 equal to 54, 12, 8, and 55, okay? And then we'll have summation. So now we will deal this one. Summation X equal 24, which is the summation of all those values, right? And then summation of those will equal to 31. And then summation of X squared, 118, 251, and summation XY. Okay. And then if we take, we can use this formula, this one, summation XY minus N X bar Y bar divided by summation X squared minus N X squared X bar square, and then summation Y squared minus NY bar square. So if you want to calculate X bar equal to what? 24 divided by 1, 2, 3, 4, 5. You can find this value, and Y bar equal to 31 divided by 5. Okay. And you can calculate this, you will find that value of correlation equal to 795. Okay, so this is how to calculate the correlation manually. Also, you can use z-score to find this one. So now, if you want to use z-score, you have to find z-score for each single value. So let's say, for example, this one equal to what? We have 5. So let's say, all right, X Z equal to X minus X bar divided by S. Okay. So for each single value here, we have to find X bar. So we have find X bar. X bar equal to I said summation X divided by N, which is equal, I believe, 24 divided by 5. 24 divided by 5. Equal to 4.8. This is X bar. And then you have also to find, which is this one. And then you have to find S, which is what? Summation x minus x bar squared divided by n minus 1. Or you can use this formula, summation x squared minus n x bar squared divided by n minus 1. If you did so, you'll find this value. Okay, then, so for the first value, it will be this 5 minus 4.8 divided by this value, you'll get this one, which is here. And then you will do the same for every single value here. So then the second one will be 6 minus 4.8 divided by 0.8366, 0.83, oh, sorry, 0.836660. You'll get this value. And then for the next ones, just change this value here, okay? So each time you will do this, z equal x minus 4.8 divided by 0.836660. And each time you will plug those values here, okay? You will get those. And then you will get those, and then multiply those values together. So you can do it yourself. So multiply this together, those together, those together, those together, those together. You'll get some values here. And then when you add them up, you will get 317. Okay. So this summation would be 317 minus n minus 1. You will have exactly the same value of correlation using z-score. But it's much easier to find it from the first formula, okay? So now for the first example, we did n only equal to 5. But what about, and so when we have n equal to 5, we got r equal to 0.795. And compare those values, this value to critical value, we conclude that no linear correlation. But the sample size is very small. That's why we did say we should increase the sample size. So when we increase the sample size to 23 instead of 5, we got r equal to 0.8, okay? So this is the data. Okay, this is the data, and then so this is the scatter plot. Okay, somehow still we have some values like far, but the rest of the data set will be very close to the very close to the straight line, right? So if we calculate, so using, if we calculate the R, and we got, and let me see if they have it here, yes. So we compare it with B value less than alpha, then we say that, yes, we say we have a linear correlation. B value greater than alpha, we say that, oh, we know we don't have correlation. So now if you look, you see here, R equal 0.8, and the critical value 0.4, so it will be like this. -1, 1, let's say he's 0. And then we have here 0.4, here -0.4, right? So we did say any value here, we have correlation. Any value here, no linear correlation. So if we check now, our value is 0.8. So 0.8 somewhere here. So using the critical value, we say, yes, we have linear correlation between those two variables. And then if we look to B value, equal, I mean, let's say very close to 0, and this value is less than alpha or less than 0.05, okay, just here. Then we say, yes, we have correlation, which is, this is the, so our value here, right? So this is the critical value here and here, and we say, yes, we have correlation here. It should be no linear correlation. Also, you can use the table. So check this one using the table. If you couldn't find the table, we can do it tomorrow in the classroom, okay? Show you how to find the value from table. So this is how to say, so we did say, okay, any value will be here or here. We have correlation, and any value will be somewhere here. We can say, yeah, we don't have or no linear correlation, okay? So no linear correlation, or we can say that we can conclude that there is not sufficient evidence to support the claim of linear correlation. Why? Because, so why we say no evidence here? Because if we change the sample size, we might get we get a new evidence or the claim, or we change our decision. You see the same example we did when we had the sample size equal to 5, we did say no correlation between those two variables, or no linear correlation. But when we did increase the sample size to 23, we did say, yes, we have correlation, or now we have a new evidence that we have to support the claim of linear correlation. Okay, I think that's it. Oh, and also now this value of R square. R square, we can call it a coefficient of determination. This R square basically is the square root of R. So we remember R is between -1 and 1. But R squared, since it is squared, it will be between 0 and 1. So this proportion, or this value, will represent the explained variation using the X. So this one should be studying after in next chapter. So now we say that, okay, so imagine imagine R squared equal to 0.6, or it will be 60%. We can say this is 60% of variation in Y because of X. Okay? So the variation of one of the variables will be determined by the other variable, but we should study this one after regression to know the independent variable and dependent variable. So now for this one here, we can say we have 23 chocolate noble data. We are getting R equal to 0.8. What proportion of variation numbers of noble can be explained by variation in the consumption of chocolate, which is about, we can say about 64%. Okay, so it's about 60% of the variation in numbers And then we have, so now we have 64% explained by chocolate consumption. But what we have left, which is 36%, we can call this one unexplained variation, or variation that we cannot explain because of two reasons. One, just chance or error. Two, because of other factors that we don't include in our study. Because here we include one variable, which is chocolate consumption, right? But the rest might we have other variables that we don't study and related to this 36%. So 36% of variation that we cannot explain because of one, random error or sampling error, okay? Two, other factors we don't study. The last thing I think here in this session, correlation does not imply causation. When we say correlation, so we say, okay, so we have a relationship between X and Y. We will not study which one will affect the other one, okay? So we will not say X will affect Y or Y will affect X. But if we study this, I mean, if we study and study the correlation between our basically in next chapter a regression, we will know which one of those variables will affect the other, okay? So here they said would be, so I like to think that eating more chocolate would help to win Nobel prizes. Even though this makes sense, but when we study correlation, we not go to this conclusion. So some errors that we, when we study correlation, which is the first one we mentioned that correlation does not imply causation. And then using the data on averages, okay? And then ignoring the possibility of nonlinear relationship. So when we get R equal to 0, might we say, oh, no relationship, which is a mistake, right? So we should say no linear relationship between those variables. Okay, so that's it for correlation. Will take a few minutes, and we will study the last one, which is regression. So much easier. We'll do this one faster since we already almost the same way of applying correlation. So just let's take 5 minutes and then we'll go back to the next session.